A study is done on a population of a certain fish species in the lake. Suppose that the population size, P of t, after t years, is given by the following exponential function. Find the initial population size. Well, in English, we could translate this into mathematical symbols. The initial population size occurs when you're about to start the stopwatch. So we usually start the stopwatch at time 0. So when t equals 0, what is the initial population size? The initial population size is translated as P of 0. So we just evaluate P of 0 and we get the answer. 420 times base 1.18 raised to the 0 power. But that's just 1, so we left with 420. Now we just answer it in a complete sentence. The initial population size is 420 fish. Does the function represent growth or decay? Well, notice the base is 1.18, which is greater than 1. Strictly greater than 1. I guess I could write a capital B here. Therefore, the model represents growth. Or we could say the function represents growth. This is an increasing function from left to right. Let's circle that. By what percent does the population size change each year? Notice the t, the independent variable t here is represented in years. There it is. And it's actually increasing at, it's measuring the increase at the end of the year. So by what percent? The t is acting on the base. Since 1.18 is more than 1, to find the percent increase, we're simply going to take the 1.18 and subtract it by 1.00. Now we get a decimal here of 1800ths. And now we want to change that to a percent. So how do we change that to a percent? We are going to multiply by 100. So if you take, actually, the percent symbol means 1 over 100. So the percent symbol means 1 over 100. In this case, that is actually equal. I don't even need an arrow here. This is actually equal. How about right below it? 18%. Yeah. Once again, we could write it in a complete sentence. The population size change each year by 18%. A car was purchased for $21,500. Each year since, the resale value has decreased by 21%. Let T be the number of years since the purchase. Let Y be the resale value of the car in dollars. Write an exponential function showing the relationship between Y and T. There's a little error here. That really shouldn't say Y. Let's fix that. This should say Y of T, because we are looking for a model, or we're looking for a function. Same thing here. That's a mistake as well. That shouldn't just say Y. That should say Y of T. The car is depreciating over time elapsed. And how much is it depreciating? It's depreciating by 21% per year. Now we do have an initial amount. So why don't we label things now? why don't we let the number of years equal time. The number of years is t. So we're going to start changing the English to mathematical symbols. The resale value is y of t. We're in good shape. We are given the initial amount. We do know y of 0, or the initial value of the car, 21,500. And this is decaying because it's decrease, so it's a decay. And we just need to know how much it's actually decreasing. Decreasing by 21%. So I'm going to translate this as 1.00 minus 0.21 to get our appropriate decimal. Our appropriate decimal is 0.79, and this is going to be our base. And for this exponential model, it's simply y of t is equal to the initial amount, which we could call y naught, y sub naught. And then we have some base. Our base amount is, let's call it b. And then raised to the t power, where t is in years. And let's substitute y of t is equal to y naught, which is 21,500. And then our base is 0.79, and then we raise it to the t power. And this is a pretty good exponential decay. You know it's decay because the base is less than 1. Let's circle that for our final answer. Let's do a little bit of chemistry here. The number of milligrams, D of H, of a certain drug that is in a patient's bloodstream H hours after the drug is injected is given by the following function. D of H is equal to 15 times base E raised to the negative 4500ths times H. When the number of milligrams reaches 7, the drug is to be injected again. How much time is needed between injections? Round your answer to the nearest tenth and do not round any intermediate computations. Let's do a quick sketch of the graph that's going on in your head. Let's say you have an h-axis, and then you have a d of h axis. And really this is a quadrant 1 graph. We do need to know what h is. H is in hours. And d of h is measured in what? It's the amount of the drug in milligrams. So this axis is really representing milligrams. And of course we can't have negative milligrams. Now the potency of the drug is actually losing potency over time. So right about here, you have a dotted line that goes like this. We actually know this ordered pair. It's called the y-intercept, 0, 15. And it's decaying, so it goes like that, right? Doesn't seem to have any vertical asymptotes, but there is a horizontal asymptote of, let's see here, y equals 0, I guess you could say. Or you could say d equals 0. The horizontal asymptote is d equals 0. It's right here, you can see it. That horizontal asymptote is labeled d equals 0. How much time is needed between injections? Well, when your very, very first injection was 15 milligrams, we need to find when it's actually 7 milligrams. So what's going on the graph? We're trying to find this question mark when this actually, well, more like here, I should say. We're trying to find this question mark when this is actually, what, 7. So let's solve for the question mark. we're trying to find that question mark. That ordered pair is question mark and 7. Typically in mathematics, we usually call that question mark x, but in this case our question mark represents an h value. So why don't we just plug things in? We do know d of h at that moment. D of h at that moment is actually 7. 7 is now equal to 15, base e, negative 0.45, and then h. So notice we're only left with an h, and we're trying to find that h. In this case, h is our question mark, or question mark is equal to h. Divide both sides by 15, because 15 is not 0, so we have 7/15 is equal to base e, negative 0.45h. We'll take the natural log of both sides. We'll use the natural log function here because it's the inverse function of the exponential function. And we have log properties, and we have the natural log of 7/15 is equal to negative 0.45h. We could divide by negative 0.45 because it's not 0. And notice we have a negative number divided by a negative number, so it's going to be a positive number. And I'm really referring to this. ln of 7/15 is negative, and divided by a negative is still going to be a positive number. And so we really want that. We don't have negative time. We don't have time machines yet. And here we go. H is equal to ln of 7/15 divided by negative 0.45. It says round your answer to the nearest tenth. I am going to box this, by the way, and put units on it, even though this isn't the final answer. This is actually in hours, I believe. Yes, this is hours. Okay. This is what we call an exact answer. Now we're going to do an approximate answer with a calculator. So make sure you can put that in your calculator, find the quantity in the numerator, and divide it by negative 0.45. Actually, before I approximate, I will go ahead and give you h as its decimal representation, 1.69364456, and it keeps going on forever. And we're trying to round to the nearest tenth, so look at the hundredths position. It's a 9, which is more than 5, so we're going to round this up. And let's answer this in a complete sentence. About 1.7 hours is needed before we can inject the drug again of what? 7 millimeters? Or sorry, 7 milligrams. It's always nice to write an answer in a complete sentence because that way you don't forget to put your units, and you're already asking yourself, does this answer make sense? Is it a decay? Are we losing amount in the drug? Are we, is it 2,000 hours? Is the drug staying in a patient's bloodstream? Hopefully a drug doesn't stay in a patient's bloodstream for 2,000 hours. That would be kind of crazy. Let's talk about saving money for college. Mr. and Mrs. Gonzalez hope to send their daughter to college in 14 years. How much money should they invest now at the interest rate of 8.5% per year, compounded continuously, in order to be able to contribute $7,500 to her education? Do not round any intermediate computations and round your answer to the nearest cent. First thing you want to note is, what does it mean to have a model that compounded continuously? We're going to translate that right away. We're going to translate that to what letter should we use? We can't translate that until we translate some of this English into mathematical symbols. So why don't we use this? Why don't we say the number of years is t, and let's have m of t be money. Or more importantly, money saved. And if it's money saved, this should be a growing account. And how is it growing? It's growing by compounded continuously. So if I'm going to use m of t and t, why don't we use m of t is equal to some initial amount, let's call it m sub naught, times base e, times a rate, times a time. I'm sorry, m sub naught, which is the initial amount, base e raised to a rate times a time. That's what I meant to say. All right. We're trying to find m naught. That's, we're trying to find the initial amount. Looking back at the problem, it says Mr. and Mrs. Gonzalez hope to send their daughter to college in 14 years. And in 14 years, we want 7,500 to be saved. Now, we know how to write that once we have the actual symbols. What those two sentences mean is m of 14 is 7,500. We're going to take advantage of this. We're going to substitute it over here in triple star. Because we also know the rate, but we got to make sure we change the rate into a decimal, which is that, and we're in business. Let's see what we could do. If we're substituting that into triple star, so from triple star, we now know that we have 7,500 is equal to m sub naught, base e times the rate, which is 0.085, and then times t, which is 14 years. Now our goal is to solve for m naught. So we can divide this by base e, 0.085, raised to the 14. Oh, divide by that on this side as well. And let's see what we get. M sub naught is equal to, got a 2281 decimal 659, and that's enough. And then there's many decimal places after that. It says round your answer to the nearest cent. So I could look at the thousands place. Thousands place is a 9, so we're going to round this up by one more penny. And let's write a complete sentence so that everything makes sense. Mr. and Mrs. Gonzalez should contribute $2,281.66 now, so that 7,500 would be available in what? In 14 years. That would be awesome. So it's always nice to write things in a complete sentence, because that way you will never forget to label the units. Whenever you're given a problem in words, you should always answer it back in words. Let's talk a little bit about some biology here. The number of bacteria in a certain sample increases according to the following function, where y naught is the initial number present and y, well, that shouldn't say y, we're going to change that. That should say y of t. Y of t is the number present at time t. How many hours does it take for the size of the sample to double? Do not round any intermediate computations, and round your answer to the nearest 10th. All right. Let's see here. First of all, let's edit some of the mistakes that are sometimes given to you. Let's edit that to be y of t. Now we know that t is actually time in hours. We also know the initial amount. Y evaluated at 0 is what we call y naught. And we know that y naught is not 0. That's going to be really, really key. Now we want to double our sample. So how do we double our sample? We're going to substitute 2 times y naught for y of t. We're going to say 2 times y naught. That's twice the population. It's now equal to y naught e to the decimal 0.059 times t. And why is it so important to mention that y naught is not 0? This is required, by the way, because in algebra you're always taught never to divide by a variable unless you know why. So it's required to state that y naught is not equal to 0. Since y naught is not equal to 0, we could divide the entire sides of the equation by y naught. So we get 2 is now equal to e to the decimal 0.059 times t. And of course, we'll use the inverse function of the exponential function, so which is natural log for this particular case. And now we have ln of 2 is equal to 0.059 times t. 0.059 is not 0, so we could divide the entire sides by 0.059, and we finally get t to be ln of 2 over 0.059 hours. Even though this is not the final answer, I'm going to box this because you always find the exact answer first before you do any kind of approximation. Now we're going to try to round our answer to the nearest tenth. So go ahead and take a calculator. The calculator says this has a decimal representation of 11.74825 ... We just got to round to the nearest tenth, so we look at the hundred spot. 4 is less than 5, so we're going to round this t to be 11.7, and we're going to, more importantly, write this in a complete sentence. About 11.7 hours is needed for the bacteria to do what? For the bacteria to double. Always nice to write in a complete sentence, so that way you don't ever forget to label your units. As a math student or a science student, you will always remember to label your units. Nobelium-259 is a radioactive substance that decays according to the following function, where y naught is the initial amount present, and y, well, that shouldn't say y, that should say y of t. Y of t is the amount present at time t in minutes. Y of t is equal to y naught e to the negative 0.012 times t. Find the half-life of nobelium-259. Do not round any intermediate computations and round your answer to the nearest tenth. Because there's a negative exponent here, you could put that negative onto the e and it'll look like 1 over e. So just imagine this for a little while. If you just see that, that's actually 1 over e, which is less than 1. And that kind of indicates that this is a decay model. In other words, this is a decreasing model. So the amount of the substance is decreasing from left to right if you were to graph this model. We need to find the half-life, not a problem. So we do know the initial amount right here is y naught, which is not 0. That's going to be a key step. And in order to get the half-life, well, we're going to put half of y naught, and is now equal to y naught times e raised to the negative 0.012 times t. Now, because y naught is not 0, we have to state it. Make sure you state it. This is required. Because in algebra, you're always taught never to divide by a variable. Never, 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 unless you know why. So you better state this why first. You have to state why naught is not divided by 0. And so that way we could divide both sides of the equation. Now, we have what? We have 1/2 is equal to e to the negative 0.012 times t. We're going to use the inverse function of the exponential function, which is the natural log. So we're going to take the natural log of both sides. And now we are left with the natural log of 1/2, which is a negative number, is now equal to negative 0.012 times t. Negative 0.012 is not 0, so we could divide the entire sides by that. And we finally get t. T is going to equal to a negative number divided by another negative number. And of course, that's good, right? We don't want negative time. If you got negative time in your answer, you obviously made a mistake. This I am going to circle anyway, or box. This is going to be measured in minutes. This is the exact answer. It's very important to find the exact answer and show how you get it. Because in mathematics, we tend to look for the exact answer before we even approximate. Now let's find a decimal representation. The calculator says this is 57.76226, and ... It keeps going on forever. It says round your answer to the nearest tenth, so we just need to look at the hundredth. 6 is more than 5, and so we're going to round this up to 57 8/10 of a minute. Almost an hour. Almost. Let's write our answer in a complete sentence. The nobelium 259 has a half-life of about 57.8 minutes. The area covered by a certain population of bacteria increases according to a continuous exponential growth model. Suppose that a sample culture has an initial area of 2.3 square millimeters and an observed doubling time of 11 days. What will the area of the sample be in 15 days? Do not round any intermediate computations and round your answer to the nearest tenth. First thing we want to do is translate some of this English into mathematical symbols. Let's take this fragment here. Well, let's take this noun. Area of the sample. Area of the sample is going to be called A of t. And we're also going to say the number of days is t. This is very, very important in mathematics. We often call t to be the independent variable and A of t to be dependent variable. And it's obviously why you could see the dependent variable, because A is dependent on time. So that's another way to read function notation. So A of t, that says A also depends on time. So A is a function of time. The independent variable is t. We're given certain things. I mean, right away we're given clues like this. Suppose that the sample culture has an initial area of 2.3 square millimeters and an observed doubling time of 11 days. That's a lot of information. They actually gave you A of 0 is equal to 2.3. They also gave you the doubling time of 11 days. So they also gave you A of 11 is equal to 4.6. So that's, once again, a lot of information. We also need to know how to translate a continuous exponential growth model. Continuous exponential growth model, with the English symbols that you have, is going to be A of t is equal to some initial amount, A naught, let's say, base E, raised to the R times t. Now we do know some of this information. We know 2.3 already. So far we have A of t is equal to 2.3. Oh, this is a sub naught. That's another way of writing a sub naught. Is 2.3 times E times R, raised to the R times t. So what we're missing is R. What is R? How do we find R? We're going to need to use this condition right here, this triple star condition. Very, very important. When t is 11, we know A of t is 4.6. So we're going to put 4.6 over here, 2.3 here, e to the r times 11, and now we're in business. 2.3 is not 0, so we could divide the entire sides by 2.3. So we get 2 is now equal to e to the 11 times r. We need the inverse function of the exponential function, so that would be the natural log. So we're going to take the natural log of the entire sides, and now we have 11r is equal to ln of 2. $11R is equal to ln of 2. 11 is not 0, so we can divide the entire sides by 11, and we get r is equal to ln over 2 divided by 11. Now, we're getting there. Key step here is that you found your model. A of t is equal to 2.3 e, where r is what? R is ln of 2 divided by 11, and then multiply by t. Circle that. That is really, really important. In fact, now I'm going to call this quintuple star. That's how important it is. I'm going to label it with 5 stars next to it. We need to answer the question. So if you've forgotten about it, go back and read it. What will the area of the sample be in 15 days? Well, once again, the function notation tells you to do everything. So we just need to find A of 15, which is just an expression. 2.3 e to the what? ln of 2 over 11 raised to the t power. Dun, 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 dun. Yeah. Let's, oh, I said A of 15. No wonder I'm staring at that looking funny. There should be a 15 there. I'm evaluating this at 15, so this needs to be 15. All right, we're in good shape. Go ahead and put that into your calculator. And we get a decimal representation of 5.91865. It says round your answer to the nearest tenth. So we look at the hundredths place. That's a 1, which is less than 5. So we're going to round this down to 5.9 days. Let's write our answer in a complete sentence. You might want to ask yourself, does the answer even make sense? If the doubling time was 11 days, and we're looking at it at 15 days, it should be more than 4.6. 4.6 square millimeters. And it is. So that's a good sign. Why don't we answer this now in a complete sentence? The area of the sample, well, I should say, in 15 days, the area of the sample. This is why we write things in complete sentences. A of 15 is not in days. That's nonsense. So when you're writing your answer in a complete sentence, you actually will not make a mistake here. So that should be what? A of 15 should be in square millimeters. Let's relabel that correctly, like the true scientist that you are. There we go. Square millimeters. In 15 days, the area of the sample is about 5.9 square millimeters. So just a quick recap here. There's a lot of things going on. In any word problem, translate the words into mathematical symbols. Words, symbol. Words, symbol. Then try to write an equation or a model, because more than likely, word problems are really about equations. And what do you do with equations? You solve them. You solve them for a missing variable. In this case, your variable that was missing was r, so you were able to solve for r, and then you go back and plug it into your model. And once you plug it back into your model, you can answer any follow-up question that might be proposed to you, or you might be wanting to make predictions, and now you can make those predictions. Once you have a model, we can use it to make predictions. What are we predicting? In 15 days, what would be the area that is covered by that bacteria? And of course, you substitute 15, you manipulate an expression, and then you get the expression that you want, and then you can make your prediction or make your conclusion. A certain substance decomposes according to a continuous exponential decay model. To begin an experiment, the initial amount of the substance is 500 kilograms. After 5 hours, 290 kilograms of the substance is left. How much of the substance is left 14 hours after the beginning of the experiment? Do not round any intermediate computations, and round your answer to the nearest whole number. What is a continuous exponential decay model? It'll look something like this, right? I mean, if you look at it, it'll probably be a quadrant 1 function, and it hits a y-intercept and starts decreasing like that. Now, we need some symbols. We really need some variables. We need some English that needs to be translated into mathematical symbols. So why don't we do that first? The time in hours is going to be the letter T. What else do we need? We need the amount of the substance. The amount of the decomposing substance. The amount of the substance. Why don't we just use A of T? So we introduced an independent variable, T, and a dependent variable called A of T. Independent variable T, the dependent variable called A of T, or you could sometimes just say A. What else do we have? The initial amount of the substance is 500 kilograms. We also know that this is going to be an exponential decay model. So if it's exponential decay, and we have A of T and T, we could write a relationship. Our relationship is going to be this. A of T is equal to A naught E, let's say, to the negative RT. And that negative symbol here is representing decay. So that's what we're going to start off first. I'm going to start off with translating our English into variables, and then recognizing what does it mean to have an exponential decay model. We also know a lot of things. We do know A sum naught. A sum naught is equal to A evaluated at 0, which is given. It is given to be 500 kgs, or 500 kilograms. We also given a certain amount after 5 hours, and in function notation that's called A of 5, which is 290 kilograms. Let's use this part second. This is our second hint. If we use that, we could rewrite A of t. A of t is now equal to 500 base e to the negative rt. And now we know what's missing. The only thing that's missing is r. So our goal right at this moment is to find r. And how are we going to do that? How are we going to find r? We're going to use this third hint. And the third hint is over here. We're going to use this a of 5. A of 5 is 290. Let's substitute that. So I'm going to put 290 here. But t is 5. And so we made another substitution. So 2 separate substitutions will help you get yourself going in this problem. 500 is not 0, so we could divide both sides by 500. And we get 29 over 50 is equal to e to the negative 5 times r. We're going to take the natural log of both sides because that is the inverse function of the exponential function. Comes in handy. And now we're going to try to solve for r. Negative 5r is equal to the natural log of 29 over 50, which is a negative number. So when you divide the entire sides by negative 5, you get a negative number divided by a negative number, which is a positive number. All right. What do we have now? Now we have something very, very important, and that is your mathematical model. Your mathematical model is a of t is equal to 500 e to the negative r, which is not negative, negative r. Times t. Yeah. And this is definitely a decay model. I guess I could simplify that. A of t is equal to 500 base e to the ln of 29 over 50 divided by 5 times t. All right, we're going to circle that. That's really, really important. Algebra is about functions and function notation. I'm going to put 5 stars next to this. Okay, we're going to use that 5-star equation, that 5-star mathematical model, to answer this question or make this prediction. How much of the substance is left 14 hours after the beginning of the experiment? In other words, can you find a of 14? Of course you can. All you have to do is plug in 14 for t and then make your prediction. E to the ln of 29 over 50 over 5 multiplied by 14. And then of course take your calculator and do your magic on your mathematical microwave. The decimal representation is 108 decimal 7848. And there's a lot more decimal places after that. It does say round your answer to the nearest whole number. So we're just going to look at the tens place. 7 is more than 5, so I'm going to round this up to 109. And we need to know what are the units. They're actually kgs. Let's answer the question in a complete sentence. After 14 hours, there is about 109 kilograms of the substance left. And remember, ask yourself, does this even make sense? Are your units correct? Are you labeling things correctly? Is it a decay? Does your answer represent a decay? In other words, is there less than what we had in the beginning? And the answer is yes, we definitely have less. Do we have less than 290? The answer is yes, we do have less than 290. So this answer does make sense. Ask yourself that. Be that scientist. Make those observations. Be curious.